السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. We'll continue talking about neural networks, of course, as we started last time. We saw different architectures. I mean, we defined what a neural network is, what are the layers, what are the units, and I think we stopped at this slide where we were talking about how we can implement forward propagation in two-layer network. What do you mean by forward propagation? Yes, the computations at each layer is based on the previous layer, so we do it in a forward way until we reach the last layer where we will get the final output of the network. Okay, so this is actually prediction or training? That's prediction, of course. Okay, we assume here that the weights are already learned and the biases, so all the parameters of network are already learned. So this is how prediction is computed. Okay, of course, this is very special case when we have two-layer network. Here's another case, and this slide we will focus on specific issue. But let me ask you first, what's the number of the layers here in that example? 3 layers, 3 or 4? Okay, we said that the layers are the layers of weights. Okay, so we have one set of weights here, a second set of weights here, a third set of weights here. So this is a 3-layer network, not 4. Okay. Type. How about the dimensions of each layer? This is usually the input layer is represented by a vector. Okay, so this is 3 by 1 vector. This is the hidden layer is 4 by 1, and this is also 4 by 1. Okay. Now the weights are represented as matrices. Okay, so this matrix is 4 by 3. Okay, so if you look at it, you will see that, let's say that this is the W1. So it's 4 rows times by 3 columns. Okay. So that's W1. Now when we compute the values of the hidden layers, of the hidden units of the first layer, we actually multiply this matrix by x. Okay. So it will be multiplied by 3 by 1 vector, which is x. Okay. Of course, will be and we will add the biases. How many biases we have? 3. No. In the first hidden layer, how many biases? 4. We have 4 units. We have 4 units here. 1, 2, 3, 4. 4 neurons. There is a bias for each neuron. Okay. Type. When we multiply W1 by x, what will be the dimension of the result? First, will that be a vector or a matrix? Vector. What's the dimension? So this is 4. Yes, 4 by 3 times 3 by 1. That will be 4 by 1. Okay. And we will add the bias, which is 4 by 1. That's the bias. Call it B1. Okay. That will give us what we call H1, which is a vector also, right? A vector of 4 by 1. So this is H1, this is H2, this is X, and this is, I think, called out in the code. Okay, so this is H1 will be 4 by 1. Okay, that's 4 by 1. So the idea here is that if you look at W1x, you know how to multiply a matrix by a vector, right? So we will multiply the first row by the vector, right? Sorry? What did you say?
So from the limit on this point, يعني rows equal 3?
No. Now to allow for this matrix vector multiplication, the rows, each row represent the weights that are going to a specific unit. Okay, دلوقتي this is x, okay? When we multiply this matrix by this vector, the first thing is to multiply this row by this vector, right? Okay, this will give us, and if you are talking about the result of this matrix vector multiplication, that will be a vector, right? Will be the first element in that, okay, in that vector. Then when we multiply this one with the vector, we get the second element. Okay, what are these elements? If we just ignore the biases for now, these will be the values of the units. Okay, يعني if I assume that the biases are zeros, just for simplicity, so multiplying this by that will give me the weighted sum for the unit, for the first unit. Okay, so this row actually represent the weights going to the first unit, which is this one, and this one. Okay, but we don't have to do it one by one. That's the idea here. In this slide, we are saying that in practice, in implementation, we don't have to do it one by one. We don't have to do it with every unit separately. We can just multiply the matrix with the vector. The output will be the vector that represents all the values of the hidden units. Okay, did you get the idea here? So let me show you the code now. So this is how you implement it. This is one way of implementing it in Python. This is the activation function. We define the activation function. Here we assume that it's sigmoid. Then this is just as an example. Okay, this is just for illustration. We are generating the input here. Of course, we don't generate the input randomly. This is coming from the training data. Okay, so that's the vector, the input vector. Then h1 equals to, first, the dot of w1 and the x. So that's the dot. That's not a dot product. That's actually matrix vector multiplication. Okay? Plus b1, that will give us the weighted sum. And then we apply the activation function. That will give us h1. So where is h1 here? Yeah, the hidden layer, the first hidden layer. Okay? So it's a vector. Vector of which values? The values of these nodes. That's the first value, that's the second, that's the third, that's the fourth. So that's why it's a vector. Okay? Then h2, very similar to h1. The only difference is that we will multiply. Here we multiply w1, right? With x. Here we will multiply w2 with h1. Right? So w2 with h1, and then we add b2. What is b2? Biases of the second. Yes, that's 1, 2, 3, 4. Okay, that will give us h2. What is h2? The values, of course, after we apply the activation function, that will give us h2. Then the output, we multiply w3 with h2. Okay, w3 with h2, it's dot product. Dot with numpy it can take matrix vector or matrix vector, or actually matrix also. Okay, so it does all of these matrix vector operations, and we add b3. What is b3? That's the bias of this. So that's b3, and the value of the output is out. Okay, any question about this? So in Python, we don't have to do the loops. We don't have to treat each node separately. Of course, you understand that this is how it works, but in reality, in practice, we just do it matrix vector multiplication, and that's it. Okay. It can even be parallelized, and if numpy is doing it, I think it is parallelized even. Okay. Yani, if you think about the matrix vector, each row can be multiplied by the vector independent of the others. Okay, so it can be parallelized. And of course, W1, W2, W3, B1, B2, B3 are all the parameters that already learned before. Type. We can even do one step further, and instead of just doing that on one example, x is a vector, we can have a batch of examples. And X here can be a matrix actually, and without changing this code at all, except of course this line which generates the examples. So X can be not just one vector, it can be a batch of vectors. In this case, it will be in columns. And each example will be a column. Okay, we put them in columns, and then we use the same code. Now, if we do that, if we have a batch of examples together, this way, the output will not be just one number. It will be multiple numbers with the number of the input examples. Okay, so that will be the prediction for each number. But instead of doing it with a loop, it will be much faster to do it using matrix multiplication and matrix vector multiplications. Okay, did you understand this? I would strongly recommend you to do that manually yourself. Yani first start with one example and do the multiplication. Of course, you can put any numbers for the weights and the features. Do the multiplication, okay, to the end, just to make sure that you understand how it works. Try it with 2 examples now. Instead of 1 example, try with 2 examples and see what will the multiplications will give you, okay, and how it will actually work for the entire network. To eventually, if you have just 2 examples, you will have 2 values, a vector of 2 values at the end. These 2 values are the predictions for the 2 examples, 2 input examples. Okay, did you get the idea from this? Any questions? Right. Now we will switch to the second maybe subtopic of this week, which is the representational power of neural networks. What do you mean by representational power? From the name, it's how powerful the network is in representing functions. Type. Are we actually trying to represent functions here? What functions we are trying to represent? Are we learning a function? What is the function? Where is the function that we are learning? How is it? Huh? Yes, but the model is trying to learn a real function. If you remember from the beginning of the semester, we said that learning can be seen as a function approximation, right? Remember, there was maybe a slide or a couple of slides about this. Okay, that machine learning or learning is function approximation, right? So that means that we are trying to learn a function that is an approximation of another function. Okay, so the model is this approximating function, right? But the original function is what? Yes, it's coming from the data. Okay, the function that actually generated the data. Okay, so when we say representational power, we want to talk about how neural networks are powerful in approximating functions in general. Okay, any function that is represented by, of course, the training data that we have. Type. The question is, what is the power of this family of functions? Family of functions is the functions that can be learned by neural networks. How powerful is that? Or in other way, the opposite way, are there any functions, any real functions, that cannot be modeled with a neural network? Is there some functions or some types of functions that neural networks cannot learn? So the answer of these 2 questions is this. So what does that say? It says that 2-layer neural networks are universal function approximators. What does that mean? First, what do you mean by 2-layer networks? A neural network. How many hidden layers in 2-layer network? 1 hidden layer only. Okay, so it's something like this. We have input layer, we have 1 hidden layer, so this is input, this is hidden layer, and then of course we have output. So this is what we mean by two-layer neural network, because we have two layers of weights. Okay? So this is two-layer neural network. Then what do we mean by universal function approximators? It means that two-layer neural network can approximate any function. It's universal function approximator. Can approximate any function, any real function, which is really great, right? Because that means that we can learn any function, whether it's complex or simple. Neural networks are able to, with just two layers, or with just one hidden layer, it is able to learn any function, or to approximate any function. This is very powerful, right? Very powerful. We can really learn any function, whether it's complex, it's simple. Type. How did we know that? From this theory. This theory says that if we have a function f, which is continuous function, on bounded subset of d-dimensional space, which means that the input to the function is finite, is in d dimensions. So in our case, the input is just the number of features. Okay, finite. Then there exists two-layer neural network, f hat, with a finite number of hidden units. So the number of units, number of neurons in the hidden layer is also finite. That approximates f arbitrarily well. So it is a very good approximation to f. In more specifically, for all x in the domain, for all training examples, or for all examples in our domain, then the actual value of the example and the predicted value of the example from the network are very close, are actually within epsilon error. Epsilon, of course, is very small value. Okay? What does that mean? Again, it means that if we have any continuous function, then with two-layer neural network, we can approximate that function, okay, with very small error. Of course, any approximation means there is an error, but the idea here is that the error is very, very small. That's what the theory is saying. Okay? There is a proof for that. Okay? I don't really know. I don't have an answer for that. Okay, so do you understand this? Do you have any question about the meaning of this? Of course, there is a proof for that. Type. That means that two-layer network is very powerful. Maybe we don't need even more, right? We don't need more layers. If with two layers we can do everything, then maybe it's enough. Just to give you an example of how powerful the two-layer network is, if you remember when we talked about perceptron, we talked about this XOR problem. Do you remember? This is the problem that we have on the slide now. The XOR problem has two classes, and they are not separable by a line. So that's why perceptron cannot actually separate. We cannot solve this problem. But with two-layer neural network, we can solve it very easily. Just two layers. And the example, a very nice example, is in the textbook, and I want you to go through it. Very important that you need to go through this example from the textbook. It shows you how, with two-layer network, you can solve the XOR problem. Okay, you can learn a classifier, neural network classifier, that can separate these two. And of course, you see here the decision boundary. Is it linear? It's two lines, actually. Two lines means it's not linear, means it's just one line. Okay, so this is not linear, of course. Okay, so perceptron or any linear model cannot solve this problem, but with just two-layer neural network, you can solve it. Okay, I want you to go through it in the textbook and convince yourself that this network with these weights will learn this function. Type. As I said a few minutes ago, if two-layer networks are so great, so powerful, can approximate any function, Why do we care about deeper networks? I am sure that you hear about deep learning now, right? Deep learning means we use deep networks. What do you mean by deep networks? More layers, okay? More layers. Not thousands of layers, usually tens of layers, maybe 5, 6, and more. This is considered deep network. Type. If 2 layers are enough, are that powerful, why do we need deeper networks? We can just stick to 2 layer. We can learn any function. We don't need even more. So the problem with 2 layers is that we don't know how many hidden units we need. It said 2 layers, but didn't say how many nodes, how many hidden units in that one hidden layer. So if we go back to this, okay, so this is 2-layer network, right? How many input units we have? That depends on the features, right? So this is given. It's the D. How many outputs? Depends on the number of classes. Usually this is few classes, right? Okay, so maybe 1, 2, 3, depending on the number of classes we have. So this is very few. This is also finite. The only thing that we don't know is how long this line is, how wide, okay, the width of this layer, how many units we have here. Okay, the theory doesn't tell us how many units. So for some problems, like this one that is also explained in the textbook, if you want to solve it, or if you want to build a classifier, a neural network classifier, to solve it, then you need exponential number of hidden units. If you just use 2 layers, okay, it's exponential number. While if you allow deeper networks, it will be just a linear number of, linear number, order of n units only. Okay, and if I have if the input is like 100, then I will need just order of 100 nodes overall in the network as a whole, if I allow more layers. So give me a minute. Okay? So let me explain this more. First, this problem is called the parity problem. This is one example of functions that will need so many units if we use just 2 layers, but will need much fewer units if we use deeper network. How does that look like? We said that first let me explain this problem. The parity problem is just very, very simple. We are given number of bits, okay, zeros or ones, and we want to know if we have odd number of ones or not. If we have odd number of ones, then the network or the classifier should say 1. Okay. Otherwise, it should say 0. Okay. It's very simple, right? We just need to count. Just to count the number of ones, actually. A 2-layer network, just to do this counting, we need exponential number of units. Okay. So many hidden units to do this computation. So it will be something like this. Let's say that we have 100 bits. So this is 100. Okay. For the 2-layer network, we will have so many hidden units. Actually, exponential number. So the number here is like e order of e to the power 100. A huge number of units. How many output units we need? Just 1. So this is the 2-layer network. Okay? How many units, how many neurons we need here? Exponential number of units. If we do it using deeper networks, it will be something like this. So we start again with the 100, right? So that's the 100 units. Then the second layer will have less number of units. Then the third will have less number of units, then less number of units, then less number of units, then 1 unit. You know the tree? It will be something like a tree, exactly like a tree. Of course, the number of layers is more than 2, right? But the total number of nodes in the network, of course, excluding the input, because these are not neurons, right? So the number of nodes here is order of 100. Now compare that number with that number. Okay, so deeper networks are more powerful. Okay, why is that? Because we are able to do more interactions for the input features to interact more. Here the interaction between the units is much less than here. Here we can use intermediate outputs from we can do combinations of operations. Okay, each layer do maybe one kind of operations, and then the second layer do one layer of operations over what we had already computed, and so on. Okay, until we reach to just one output that we need. So the number of operations will be much less than if we just do it in one layer. Okay, is that clear? طيب, why do we care about the number of neurons? Why should we care about the number of neurons? Less calculations in terms of prediction, right? But how about training? Training will take more time. Why? How many parameters we will have? Huh? Yes, here we have exponential parameters, right? Because the number of units here, if it's exponential, then the number of weights here is just 100 times that number. Okay, so it's the number of parameters is completely different. It's much more here than here, right? And of course, if the number of parameters is more, then we need more or less training examples. More or less, if we have more parameters to learn, do we need more training examples or less training examples? Of course, more. Okay, and more training examples means more time. Okay, of course here it's exponential. Okay, so much more time than the time to train this network. Okay, so that's just one example, of course, to show you that sometimes we have problems that can be solved in much simpler way if we have multiple layers. Okay? Can I erase this? Do you still have the question?
I have a general question. Is there a limitation to the number of hidden layers? Or the two?
Very good question. So the question is there any limit on the number of units within the layer? Theoretically, no. But practically, of course, yes, because that means more computations. Okay? So it depends on your computing power. But theoretically, no.
So I can have any number of hidden layers?
You can, but you cannot specify it to be infinite. It has to be a number. Okay? And of course, you will have to consider the hardware that you have that will be computationally capable of doing it. Yes?
I understand why this is different on this, but in the previous lecture you said we can do parallel calculation using one given layer, and then having multiple layers will make us quite.
Still with that, if you would just think about the number of the neurons, still even if you have parallelization, you still need much more time here. Yeah. So the question was, if in I think a couple of slides earlier, we said that we can parallelize these computations. So is it still worth it to have more layers if we can parallelize already, even if we have 2 layers? The answer is yes, we still, even if we do this parallelization, the difference in time is very clear. Okay, so this deeper network will be much more efficient than the other one. Yes.
This is also general question. This is not a machine learning problem.
very good note. It's a circuit problem actually, okay? But it is, we can see an analogy between a circuit and a network. There is an analogy, okay? So we can think of it as a classifier. Okay? But yes, it's not a classification problem. It's actually, it can be done by a circuit. Actually, we do it in, I think those of you who are computer engineering, you do circuits like that, right? So yes, but if you think of neurons here as gates, okay, then it's the same problem. It's like it's same design problem. Yes.
دكتور هل احنا هنتعلم ازاي
I don't know if I repeated the question or not. I think in the answer the question was clear.
هل هنتعلم ازاي نجيب الاكسبوننشال او
Okay. The question is, I think the maybe better said, how will we learn the number of, how will we get the number of neurons? Okay. I thought that we will have time to answer this, at least, if not today, we will answer that next time, but I hope that we will do it today. Okay, can we move on? Let me erase this. So constant depth circuits are less powerful than deep circuits or deep networks. The number of parameters, I think we discussed that. A deep model could potentially require exponentially fewer examples to train than a shallow one. Type. If deep, now we said that, okay, deep networks are much better, right? Much more efficient. Then maybe we don't need 2 layers, right? So we started with the opposite question. 2 layers are great because they are very powerful. Then we said that, okay, they are powerful, but maybe they will take much longer time in training. We need a deeper network so that we can avoid this excessive training time. Does that mean that we don't need 2-layer network? خلاص? Maybe we can do everything with deep. That's the question here. If deep is potentially so much better, why doesn't everyone use deep networks? Which means that still we are using shallow networks. They are used.
increasing complexity
One, that some problems don't need that some problems are not that complex. Okay, maybe also some problems we don't have enough training data, because as you add more layers, you will increase the number of parameters. Okay, if you don't have enough training examples, then you will overfit. You will have an overfitted model. But here I have 2 answers. One that is kind of related to what we studied before, which is that with deeper networks, we are introducing now more hyperparameters. What are the hyperparameters that we are introducing? The number of layers and the number of neurons or units in each layer. Okay, so that's touching your question about how we will learn that. Now let me ask you how we would do that. How would we know the number of layers and the number of units in each layer? These are hyperparameters, right? How do we tune the hyperparameters? We have to use the diff set. Okay, so this is not learnable. What is learned by the learning algorithm are the parameters, which are the weights and the biases. Okay, but these things are not learned, so you have to tune them. So in deep networks, we have these parameters, hyperparameters. We have to tune them. That means that it is more challenging. Okay. The second reason, I will not be able to explain it now, but just keep in mind that with deep networks, we will have problems in computing the gradients. Okay, and we'll talk about that inshallah next week. Okay, so there is a problem with what we call backpropagation, which is the method that we use to compute the gradients. We'll talk about it later. So for these 2 reasons, sometimes we prefer shallow networks, like 2 or 3 layers. And this is, of course, a very active research area, is how to train deep networks. Lots of studies or research studies on this. In practice, what should we do? Should we go deep or should we go shallow? So the rule of thumb or the heuristic here is that you should go deep, but not very deep. Okay, so maybe you should go to 3 or 4 layers. After that, you will not get so much improvement. Okay, except in some cases. Actually, the clear case that that is known is what we call convolutional networks. Have you heard about CNNs or convolutional neural networks? Usually, this type of networks is used for image processing, and with images, you need multiple layers because of the concepts that are learned in each layer. So, for example, if we are trying to detect humans in an image, these layers will represent a layer of features that are extracted from the image. So, for example, the first layer might detect edges in the image. The second layer from these edges will detect eyes and noses and mouths and so on. The third layer maybe detect faces from the previous layer and so on. Okay, so in images or in detecting objects from images, you actually need it's intuitive to have or to need more layers. So in convolutional networks, of course, we have much more layers than usual. Again, this is a research area also. Setting number of layers and their sizes, I think this is exactly your question, and I think we kind of answered it, right? So we need to do tuning. There's no gold answer here. But let me show you examples of issues that are related to the number of units. So let's say that we want to classify. We have a classification problem here with the red and green circles. These are the examples from two classes. And we want to train a classifier that separates them. Okay? So with three, let's say that we are talking here about two layers only. So just one hidden layer. So here we are changing the number of hidden units. If we use just 3 units, we can get something like what you see on the left figure. Is that very good classifier? Probably not. It misses some examples here, right? So with increasing the number of hidden units, we are increasing the capacity of the network. We are increasing the number of functions that the network can learn. So with that, the network maybe learned more. Okay, so it had a more complex decision boundary now. Okay, type. If we increased it to 20, we have something like this. This is perfectly classifying the examples. Is there any problem with that? Overfitting, of course. Okay, you see the decision boundaries now is very complex. Okay, it tries to fit every single example. Of course, neural network is powerful. It can learn very complex decision boundaries, but of course that can lead to overfitting. Type. To avoid overfitting from that slide, maybe we should not go into more neurons, right? Maybe we prefer smaller networks, right? So maybe smaller networks are preferred. The answer is no. Okay, the answer is no. We can, to avoid, if the problem is overfitting, we can avoid overfitting with ways specific to avoid overfitting. And actually, we discussed one before. What did we do before to avoid overfitting? Any technique that we use to avoid overfitting? Regularization. Yes, regularization. Okay, so that's one way. And we will learn, inshallah, next week other ways specific to neural networks that we can use to avoid overfitting. So the idea here is that instead of decreasing the number of units, decreasing the number of units would decrease the capacity of the network, would decrease the space of functions that the network can learn. So if we are afraid that we will have an overfitted model, then we should use the methods that will avoid the overfit. So here we actually used, with the previous example, with 20 hidden units, we used regularization. Okay? So with small regularization, with 20 units, we got this model. If we increase the regularization, we got this model. Which you think is better or worse than this one? Which is better, this one or this one? Second. Why? Simpler, which means more general. Okay, so it's more generalizable, and maybe this is even better, maybe. Okay, with increasing the regularization. This is all with 20 hidden units. Okay, so even with 20 hidden units, we saw in the previous slide that it was overfitting without regularization, without any way to avoid overfitting. Then here we have a regularizer, so we made a balance. Okay, it is flexible, or the capacity of the network is high. It can learn more functions, but it is regularized to avoid overfitting. So you should not be using smaller networks to avoid overfitting. Instead, use bigger networks as much as you can, of course, as the budget. Budget here means time and the data set, of course, and a computational power, of course, yes. Okay, computational power. Plus regularization. So you should use some method to avoid overfitting. Any question about this? Okay, what is remaining in the network session, in the neural network session? Did we cover everything that we should learn? Training. Okay, as usual, we first go through the prediction and how the network actually works and the architecture of it, and then we'll switch to training, inshallah, from the next lecture. Assalamu alaikum.